Have you ever walked along a beach and taken a deep breath? That distinct, slightly sulfuric scent you might call the smell of the sea is not just salt water, it is the aroma of a powerful climate-shaping molecule called dimethyl sulfide, or DMS for short. This unassuming gas is a global force, born from the tireless work of some of the smallest life forms on our planet. In the vast, sunlit upper layers of our oceans, countless microscopic organisms known as phytoplankton are constantly engaged in the business of life. They are the foundation of the marine food web, photosynthesizing and creating energy from sunlight, just like plants on land. The production of DMS is a fascinating consequence of this microscopic drama. When these phytoplankton are eaten by other tiny creatures or when they die and decompose, a compound within their cells breaks down, releasing DMS. This gas is highly volatile, meaning it readily escapes from the seawater and wafts into the atmosphere. Think of it as the ocean exhaling. Each year, phytoplankton release an astonishing amount of sulfur into the air in the form of DMS. We're talking about millions of tons. This single, natural process accounts for more than half of all the natural sulfur emissions on Earth, a testament to the immense collective power of microscopic life. This process connects the living ocean directly to the air we breathe and the sky above. It's a beautiful, intricate cycle. The phytoplankton, quietly going about their existence, are not just feeding the oceans, they are actively changing the composition of our atmosphere. The DMS they produce is a chemical messenger, carrying a signal from the biosphere, the world of life, into the non-living realm of atmospheric chemistry. This molecule, responsible for a smell many of us associate with a day at the beach, is a key player in a planetary-scale story of balance, feedback, and climate regulation that scientists are still working to fully understand. The sheer scale of this operation is hard to comprehend. Imagine the entire surface of the world's oceans, teeming with life too small to see, all collectively breathing out this one gas. This isn't a small, localized event. It is a global phenomenon that has been happening for eons. The smell of the sea is, in essence, the smell of life itself, a reminder that our planet's systems are deeply interconnected. The biology of the deep blue sea has a direct and profound impact on the clouds that drift across the sky, linking the smallest organisms to the largest weather patterns in a delicate, planetary dance. Once dimethyl sulfide escapes the ocean's surface and rises into the atmosphere, its journey has only just begun. It embarks on a remarkable transformation that has profound consequences for our planet's climate. High up in the air, the DMS molecule is exposed to oxygen and sunlight. Through a series of chemical reactions, it oxidizes, which means it combines with oxygen to form new compounds, primarily sulfate aerosols. These are not gases anymore, but incredibly tiny, solid particles suspended in the air. They are so small and light that they can float in the atmosphere for days or even weeks, traveling vast distances on the wind. These sulfate particles play a crucial role. They act as cloud condensation nuclei, or CCN. For a cloud to form, water vapor in the atmosphere needs a surface to condense onto, something to grab hold of. Without these microscopic seeds, it would be much harder for water droplets to form. Think of it like dew forming on a blade of grass. The sulfate aerosols from DMS are perfect for this job. They are like tiny magnets for water, attracting moisture and allowing it to gather into the droplets that, when clumped together by the billions, become the clouds we see. This process is especially important over the open ocean, where other sources of condensation nuclei like dust from land or soot from fires are scarce. Out in the vast, empty expanses of the Pacific or Atlantic, DMS from phytoplankton is the primary source of the seeds needed to make clouds. More DMS means more sulfate aerosols, which means more individual water droplets can form. This doesn't just create more clouds, it creates denser, brighter clouds. With more nuclei to spread the water around, the droplets are smaller and more numerous, making the cloud more reflective. So, this gas, born from tiny ocean life, becomes the architect of clouds. These clouds, in turn, act like giant white umbrellas for the planet. They are highly reflective, bouncing a significant portion of incoming sunlight back into space before it can reach the ocean's surface and warm it up. This phenomenon, known as albedo, is a critical part of Earth's natural cooling system. Without the clouds formed by DMS, our planet would be a much warmer place. The quiet work of phytoplankton, therefore, provides a global air conditioning service, a cooling effect that helps to moderate Earth's temperature. The cooling effect of DMS-driven clouds is not a minor detail, it's a force of nature on a scale that rivals our own impact. Some estimates suggest that this natural cooling process counteracts a significant amount of the warming caused by human greenhouse gas emissions. This raises a monumental question. What will happen to DMS production as our climate continues to warm? The answer could dramatically alter the speed and severity of future climate change. But right now, the scientific community is facing a fascinating and urgent puzzle with two very different possible outcomes. One camp of scientists, using sophisticated computer models, predicts a worrying trend. A 2024 study suggested that as the oceans warm and carbon dioxide levels rise, phytoplankton populations might change in ways that cause them to produce less DMS. A decrease in DMS would mean fewer sulfate aerosols, leading to fewer and less reflective clouds over the ocean. This would create a dangerous feedback loop. A warmer world leads to less DMS, which leads to fewer clouds, which allows more sunlight to warm the planet even further, accelerating the warming we are already causing. It's a scenario where a natural cooling mechanism begins to fail when we need it most. However, another major study published in 2025 painted a completely different picture. This research, using an even larger data set, found that while DMS concentrations in the seawater itself might decrease, the amount of DMS escaping into the atmosphere could actually increase. This could happen if warmer surface waters and stronger winds make it easier for the gas to vaporize and enter the air. In this scenario, a warmer world would lead to more DMS in the atmosphere, more cloud formation, and a stronger cooling effect. This would act as a stabilizing negative feedback loop, where nature pushes back against warming and helps to slow it down. This debate highlights the complexity of our planet's systems. It also connects to a grand idea from the 1980s called the Claw hypothesis, which proposed that ocean life actively regulates Earth's climate through DMS. This is a component of the even broader Gaia hypothesis, which envisions the entire planet's biosphere as a single, self-regulating system that works to keep conditions stable for life. Are the phytoplankton our unwitting allies, working to cool the planet as it heats up? Or is this system more fragile, at risk of breaking down under pressure? The answer remains one of the most important questions in climate science today. The story of Dimethyl Sulfide doesn't end at the edge of our own atmosphere. Its significance stretches out into the cosmos, into our search for life on other worlds. On Earth, as far as we know, DMS is produced exclusively by biological processes. There is no known, major, geological or non-living chemical reaction that creates this gas in our atmosphere. This makes it a potential biosignature, a chemical fingerprint that could signal the presence of life. If we were to detect DMS in the atmosphere of a distant planet, it would be a tantalizing and potentially revolutionary discovery. This is no longer just a theoretical idea. In 2023, astronomers using the incredible power of the James Webb Space Telescope announced the possible detection of DMS in the atmosphere of an exoplanet named K2-18b. This planet is a fascinating candidate for life. It's a sub-Neptune world, larger than Earth, and it orbits within its star's habitable zone, the region where temperatures could be just right for liquid water to exist on its surface. Many scientists hypothesize that K2-18b could be a Hycean world, a planet covered by a deep global ocean with a hydrogen-rich atmosphere. The detection of DMS on K2-18b is still tentative and needs more confirmation, but imagine for a moment what it would mean. If there is DMS, there might be something like our phytoplankton, a vast alien biosphere churning away in a global ocean, exhaling a gas that changes its planet's sky. The same molecule that gives our seas their characteristic smell could be the very thing that tells us we are not alone in the universe. It's a profound thought. The chemistry of life on Earth could provide us with the clues we need to find life hundreds of light years away. Whether we are looking outward to distant stars or inward at the health of our own world, understanding dimethyl sulfide is crucial. Here on Earth, solving the puzzle of its future is vital for accurately predicting the trajectory of our climate. We must determine whether this natural process will help us or hurt us in the coming decades. And in the grander cosmic theater, this simple molecule may one day be the key that unlocks one of humanity's oldest questions. From the smell of the sea to the clouds above and the stars beyond, DMS connects life, climate, and the cosmos in a truly magnificent way.